Now let's see about the internal resistance of a cell. Now what is meant by resistance? We know that resistance is nothing but it is the opposition to the flow of charged particle. In the case of our consideration of this electricity, we generally take as this charge as electron. So opposition to the flow of free electrons in the conductor, we simply call it as what? Resistance, right? And this resistance, now this is concerning about a cell. You know that inside a cell chemicals are placed inside a cell, and that inside the cell chemical reactions are taking place, reduction and oxidation are taking place. We call it them as redox reactions. Got it? So due to those chemicals, okay, those, if it is connected with this circuit like this, suppose your cell here and external resistance here through this connecting wire, if you make a circuit, then what happen? The current will be flowing here like this, conventional current I mean, but electron will start flowing from this negative electrode through the external circuit and it comes to this positive terminal, right? And what happened? This external circuit is completed, current is flowing opposite to the motion of those free electrons starting from the negative terminal of the cell through the external circuit, and it comes to the positive terminal. This is outside the circuit, so we call it as external circuit. But inside the cell itself, the ions are moving from the positive plate to the negative plate inside the cell itself. So those opposition, the opposition, okay, offered by the electrolyte, the chemical present inside the cell, the opposition offered by the electrolyte when ion moves from the positive plate to the negative plate inside the cell itself, we call it that opposition to the flow of ions inside the cell itself from one electrode to the another electrode. We call it that as what? Internal resistance of a cell. So it is inside the cell, so we call it as internal. Why we call resistance? Ions are moving from one plate or one electrode to the another electrode. So inside that cell itself, when ion moves from one electrode to the another electrode, they what? Face some opposition. That opposition to the flow of this ion from one electrode to the another electrode inside the cell itself, we call it that as what? Internal resistance of a cell. So there are various factors, okay, there are various factors which affect this internal resistance of a cell. It depends upon the nature of the chemicals, or rather the electrolyte that is placed, okay, so as to make that as a source of EMF. It also depends upon what? Depends upon the nature of the electrolyte. As I said, it also depends upon the distance between the two electrodes in the cell itself. If the electrode is very close to one another, then what happen? Less length need to be moved by the ion from one point to another point, right? If these two electrodes, if they are very close, then what happen? The opposition will be less. What happen? Internal resistance will be less. If these two electrode, positive electrode and a negative electrode, if they are very far away, then what happen? The ions need to move for a longer distance. So in that case, what happen? More opposition to the flow of this ion. So what happen? Your internal resistance will be high. Got it? And if your electrolyte, okay, if it is of that of the nature that it can flow these what ions very easily, then internal resistance will be less. Got it? And it also depends upon the common area between these two electrodes. Okay, if you are having two say suppose plates, okay, you must be remembering in the case of Niclan cell or Daniel cell, if you are having that electrode as just like a thin plate, okay, then what happen? The common area of the two electrodes, okay, either it may be what zinc or copper. In the case of what Niclan cell, this what your positive plate will be a carbon one, and this negative plate will be a zinc plate or zinc rod. So the common area between these two electrodes, okay, smaller of these two electrodes, suppose if your zinc is smaller than that of your carbon, then the smaller one, the area of the smaller electrode will be the common area. Okay, so larger the size of the electrode, lesser will be the internal resistance. Why? Because more and more ions may be allowed to flow from those electrode to the another electrode. Got it? So what happen, larger the area, that means common area, less will be the what, internal resistance. So your internal resistance is inversely proportional to the common area. Smaller the common area, then what happen, larger will be the internal resistance. Got it? And it also depends upon, lastly, it also depends upon the nature of these electrodes. Okay, whether these electrode can easily gives out or emits out that ions readily from those surface of these electrodes, or whether they are not readily emits those ions or electrons from those electrodes. So it depends upon the nature of the electrode also. So all these different factors affect what the internal resistance of a cell. It is also given here. You can pause this video and you can note down. Okay, it may be asked in the practical exams also. Practically you need to know it. So let's try to find out the relation between the internal resistance and that of this EMF and potential difference. The relation between what internal resistance and what internal resistance with that of EMF and the potential difference of a cell. Now you can do from here like this. As I told you that EMF is the maximum potential difference, and the maximum potential difference will be equal to the potential difference across the ends, okay, of the two electrodes when the current is passing or drawn from the cell, plus the potential difference developed, okay, inside the cell itself. Suppose we can't draw that internal resistance inside the cell itself, rather we take it outside. Okay, if you want to draw, then we can draw like this also. Suppose if you are having two electrode, for example, like this, two electrode of a cell, okay, you take it that this is the two terminals of the cell. So you take it these as positive, let me take it little bit longer like this, okay, just to represent the cell, and this side is negative. So what happened inside outside the external, outside the cell itself, I mean in the external circuit, you will have these resistors, no doubt. Got it? Capital R. Got it? So inside the cell itself you can have that internal resistance here, and that internal resistance we denoted by small r. Okay, so there is a resistance in between the two electrodes of the cell, okay, inside the cell I mean. So what happened, the potential difference across these two electrode, okay, will be equal to what, this potential difference and the potential that is developed across this when there is no current passing through it. Suppose when there is no current passing through it, means the key will be off somewhere here. Okay, when it is off, the potential difference developed there, we call it as E, right? Now when the current is flowing like this, the potential difference across this R will be the potential difference across the two electrodes of a cell, right? When the current is flowing, what happened, the potential difference here at the two electrode will be also equal to the potential difference here or drop here. Got it? Across the resistor. So what happened, your current, okay, will be flowing in this way. So the potential difference across this R, okay, and the potential difference across this internal resistance, the sum of these two potential difference across the cell or across this resistor, we will call it that as simply V, and the potential difference across this internal resistance R, that will be denoted by small v. Okay, so your maximum EMF or the maximum potential difference we call it that as EMF. This EMF will be equal to the sum of the potential difference, okay, of a cell plus the potential difference, okay, across that internal resistance. Got it? So if you make it that V is equal to IR, suppose if the current flowing here is capital I, then what happened? The potential difference across these two resistors, the two terminals of the resistor, will be equal to the potential difference of the cell. So we can write V is equal to IR from Ohm's law, and the same current I will be flowing here across this internal resistance also. So we will make it that what V small v as I into small r, where I is the current that is flowing through this circuit, okay, like this. Whatever the current that is flowing outside, that much current will be also flowing inside the cell within the electrolyte, okay. So if you take it that I common, then you will get like this. So the relation between what your current, internal resistance and EMF or the external resistor, that will be given by this relation. And if you want to relate this internal resistance in terms of what your EMF and potential difference, then it will be like this. Think that your EMF is denoted by V, potential difference by V, then we know that EMF is greater than the potential difference of a cell. If you want to know how much it is more, then you have to take a difference, right? Okay, so E minus V is a difference in the potential difference. That much potential difference across the internal resistance, okay. Symbolically, we generally draw like this, okay. Cell, internal resistance drawn outside. Got it? So the EMF, the potential difference, or the maximum EMF, we call it as simply EMF. So EMF is more than the potential difference of a cell. So by how much it is more, the potential difference or the potential drop across this internal resistance, okay. So the difference will be equal to what? IR, the potential drop across the internal resistance. So if you divided this E minus V by R, by I, that means I means what? V by R, okay. V is equal to IR, so your I will be what? V by R, right? So if you divide it, then you will get just like this. So your R will be equal to what? E by V minus 1 whole into what? R. This relation is very important and you need to remember this, because what happened in the case of this potentiometer, okay, we will learn later on that potentiometer. So this internal resistance can be measured by what? By using your potentiometer, not by voltmeter, okay. Voltmeter will not give you the correct reading of that internal resistance, or rather EMF, but your potentiometer will give you the actual measurement of either your EMF of a cell or internal resistance of a cell. That can be done by using what? Potentiometer. So while doing that potentiometer, this formula need to be remembered at that time, okay. So E by V minus 1 whole into what? R. Got it? So this is the what? Circuit equation. Got it? You can call it. Yes. Now let's see about the internal resistance in a different form. That means your internal resistance and the external resistance with that of your EMF and potential difference of a cell, it will be related like this. This is very easy. You just go through it, pause the video and you just go through it, okay. This is very easy, no need of much explanation, okay. But I'm going to tell you about that EMF and potential difference with this diagram, okay, that I have already told you. Now this is the what? Resistance box. That means resistance box is for what? Just to prevent a large current flowing through the circuit, okay. Instead of going the large unknown current, we usually place a resistance box, high resistance, in the circuit, so as not allow to pass a non high current, okay, just to prevent it. So you can take it this as capital R, the external resistance in the circuit, right? This is a cell, okay. The potential difference across the two electrodes, okay, that will be measured. When no current is drawn means when the key is what, open, that means your circuit is open circuited. Okay, so when no current is drawn from the cell itself, the potential difference across the two ends of these electrodes, that will be measured or called as EMF of a cell. But I'm telling you that your potential difference measured by using voltmeter will not give you the correct reading. Okay, instead we can use it for measuring EMF. We can measure what, the potentiometer. Why? Because potentiometer will give you the accurate reading than that of the voltmeter. Why? Because voltmeter draws some current, because it has its own what, resistance, it has its own coil there. Okay, so some current will surely be drawn from this cell itself, but in the case of potentiometer, no such current will be drawn from the cell. Okay, now in the case of potential difference of a cell, what happened, this key will be closed. Okay, key will be closed and the circuit will be there in the external circuit, so some current is drawn from this cell itself, okay, through the external circuit. So during that time, what happened, the potential difference across the two electrode of a cell, we call it simply as potential difference of a cell. Got it?